Hello, I'm Professor Steve Miller. Today I want to talk about the Baldwin and Lomax turbulence model, which was created in 1978. This particular model is a modification of the Cebeci and Smith model, which was made a few years before. The Cebeci and Smith model, which was discussed in a previous video, is not really a closed turbulence model as it needs a prior knowledge of, say, parameters that should be derived from the flow. For example, the boundary layer thickness and displacement thickness. These would have to be estimated in some way before the model is computed to find the solution. Baldwin and Lomax, indeed, in 1978, overcame these difficulties by removing them and making those parameters dependent on the field variables themselves in their calculation, removing this modification. Cebeci and Smith's model is also for boundary layers that are relatively well behaved. This particular model is also applicable to wakes, which is something perhaps like a wake behind a backward facing step, for example, or a cylinder flow where there's a wake. The flow goes from left to right in both cases. The particular model and coefficients I'm going to show are the base ones, and it's been calibrated for flows which have a pressure gradient of approximately 0 in the streamwise direction, that's partial P partial X of about 0, and of course roughly in the transonic regime. Let's start looking at the particular model. Now, we'll look at the turbulent viscosity in the inner layer first. In fact, it is exactly the same as Cebeci and Smith's model, except we've interchanged the particular term of partial u partial y by the modulus or magnitude of the local vorticity omega, which is vorticity. And just to remind our viewers what that is, a magnitude or modulus of vorticity omega is nothing but partial u partial y minus partial v partial x squared plus partial v partial z minus partial w partial y squared plus partial w partial x minus partial u partial z squared, all square root. So you see this is just the three components of vorticity, squaring them and taking the square root, typical vector calculus. So now that we define vorticity, we can give the definition of Baldwin and Lomax inner turbulent eddy viscosity, which is nu sub t, right, for turbulent in the inner part, which is sub I, equals to some length scale squared, local length scale, times the magnitude of the local vorticity. Now, the turbulent viscosity, or the eddy viscosity in the outer layer of the turbulent boundary layer will be modeled as, oops, and I want to give this an equation number, 34 and 35. Nu sub t for eddy viscosity in the outer part of the layer is equal to a constant alpha times another constant C1 times a function, empirical function, which is tuned, wake, and they call it wake because it handles wakes, times the intermittency factor. Let's define these particular constants now. Baldwin and Lomax say that alpha, calibrated for transonic boundary layer flows with no pressure gradient that are attached, will be about approximately 0.0168, and C1 will be equal to 1.6. We need to still define this function f wake right here. So let's do that now. F wake, Baldwin and Lomax propose as the minimum of the values of y max, f max, or C2 y max of u squared diff all over f max. To fully understand the formulation of this function, you'll have to look at the original paper. And here I should write, this is a C2. We'll let C2 also be a constant, which is calibrated 0.25. Let's note that this is the minimum function, which is right in Fortran. And it basically says we evaluate y max and f max, and also evaluate C2 y max of u squared diff over f max, and take the smaller value and set that to be f wake. So how do we do that, and what are these functions? Well, of course, we need some function of Fy first. Let's define that before we define F max. There'll be F of y is equal to y times the magnitude of the vorticity times 1 minus exp of negative y plus, which we defined earlier in inner coordinate, divided by square root a plus. And we defined these in our previous lecture. And we'll give another definition of a plus in a second to complete the lecture. This exponential term in Fy is completely omitted if a wake flow is concerned. So this is equal to 0 for wake calculations. Now the quantity F max right here is a maximum value of the function Fy, and y max is the value of y at which the maximum function occurs. So of course F max simply equal to the max value of f of y. And that corresponding y max will be equal to F max at y. No problem. So you see, also we have this function u diff, which we didn't define. We have C2, we have y max and F max now, but what is u squared diff? So u diff, and diff stands for difference, is the difference between the maximum and minimum total velocity. So max of u of y minus the min of u of y. And we'll put magnitudes here because this is a nice, well-behaved boundary layer. Here, u of y, just to be complete, will be equal to square root of u squared. Oh, that's a u, excuse me. Square root of u squared. U squared plus v squared plus w squared. Let me just try and erase that. There we go. Now we have it. Excuse me. So to close the model still, we need that a minimum total velocity will be 0 for the boundary layer along with fixed wall, because of course at the wall of the boundary layer we have the no slip condition of u equals 0. So we can just set this whole term here equal to 0 for boundary layers. But of course in a wake we wouldn't have such a luxury because we're not attached to a wall. It's a free flow without boundaries in the wake. We still haven't defined the intermittency, which is gamma. So if we come back here, we'll see that the last term is gamma. And we defined that in the Cebeci Smith model. Remember, that's like a value between 0 and 1, and they define it very much like the Cebeci and Smith model. So compared to the Cebeci Smith model we showed previously, it's gamma equals the quantity 1 plus 5.5 of C3y divided by y max to the 6 all to the negative 1. So this is 1 over this whole quantity, of course, in the brackets. So you'll see we have not defined C3. That's another calibration coefficient for sonic turbulent boundary layer, and that's equal to 0.3. Once again, the switch between the inner eddy viscosity is equal to nu T outer, where they are equal. And now we can maybe make some comments about this model, and we defined all the particular terms. We first note that for most cases of boundary layer flows, where basically these models give pretty much the same result, except of course the Baldwin and Lomax model doesn't have these explicit definitions of, say, theta and delta sup star before the calculation begins. This model can also be tuned for other types of flows, but it is indeed tuned for transonic flows. This model is able to calculate for many years excellent flows involving airfoils at operational flow conditions. Thanks very much for your time today. I'm Professor Steve Miller.